So this is chapter 5 on radiation and spectra. We are taking a little break from sun, earth, moon, sky, astronomical events, and we'll look little more detail into the physics of light or radiation, atomic spectra, the electromagnetic spectrum, what that is. And so this is uh, more of physics of light. And light is a wave that you'll see in a minute. And so we'll look into the physics of these waves. Light travels as a wave, similar to water waves, sound waves. And so we will, look at the microscopic view of the light waves. This is where we stopped last week. We're studying the electromagnetic spectrum, the whole spectrum. Here, starting with gamma rays, these are the shortest wavelength, highest frequency waves, the most energetic waves that we know. Very harmful to the tissues, living tissue. Here it's the wavelength range no longer than 0.1 nanometers. They are usually in the interior of the stars or during the stellar collision or supernova explosion. They can also be created using using unstable atoms. Next, energetic waves are the X-rays. They are a little weaker than gamma rays. Their wavelengths range from 0.1 nanometers to 20 nanometers. X-rays can penetrate through soft tissues, yet they get reflected from the hard tissues like bones. Hence, these are widely used rays to get the X-ray of our body. Usually, when one breaks their bones or need to check what's inside of a body, the X-ray astronomy is like optical astronomy. We use optical telescope to see the light rays, the visible part of the light coming out of the other planets or stars. At the same time, all these stars are generating all sorts of electromagnetic waves. So we can specifically look at how sun looks. Sun appears to be when we only image it through the X-rays. This is the X-ray map of the Milky Way galaxy. The one with other multicolors we are used to with seeing in the optical range. This is in the X-ray range. Similarly, there are other pictures of the sun in the gamma region as well. Okay, so we usually think of astronomy as in terms of optical range, because that's what our eyes is used to see from blue to red. 400 to 750 nanometer wavelength range. But the light coming out from the sun or outer space, covers the whole spectrum. We don't see it, but we can make detectors, cameras, to detect these different wavelengths and see, re-image it based on the energy and temperature, and see how different stars, different galaxies, different supernova explosions appear in different parts of the spectrum. This UV and visible light, we are most used to with it. Infrared, microwave, radio waves are far right or left, depending on where you start, but these have the maximum wavelengths, minimum frequency, and smaller frequency of a wave means those waves are less energetic. So radio is on the one extremum, lowest energy wave. Gamma is on the other extremum, highest energy wave. So electromagnetic spectrum, it covers here 30,000 meter wavelength, radio region to few nanometers. That's close to picometer, 3 times 10 power 12 meters gamma ray. So this all is the electromagnetic spectrum, and somewhere in there lies a very tiny minuscule region that extends from 750 nanometer to 400 nanometer. That region is the visible light region, meaning any electromagnetic spectrum with these wavelengths are only detected by our eyes, and that energy information is sent to our brain, and our brain interprets that energy with and associates with different colors. And that's how our eyes evolved, that's how we evolved. And the main reason is that because the atmosphere, Earth's atmosphere, stops most other wavelengths, other spectrum, or other part of the spectrum, the atmosphere only allows this wavelength waves to enter the atmosphere. And when humans evolved, or from single cell, our eyes evolved to detect that region only. And so here are other information where each of these waves are generated, created, and that's the conclusion. Although visible light is what most people associate with the astronomy, all other these regions are equally important as well, that we will see today. And we'll see that. So today we'll associate temperature with energy and wavelengths. So any star, so stars are the primary source of light and primary source of all the electromagnetic radiation that we know, and that again extends from radio to gamma. Okay, and what determines these different part of a spectrum, or what determines the electromagnetic spectrum emitted by stars, is dependent on the temperature of those stars. What is temperature? We say, it's 75 degrees Fahrenheit today, or we can talk in terms of Celsius, which is a standard unit. 0 degrees Celsius is when water freezes, we know that, and 100 degrees is when it boils. So, but what is temperature? Okay. Temperature is the measure of the energy of the electrons, or let's look at bigger scale, the energy of the atoms and molecules given off during the collision. So for a gas, when you say certain temperature, so that means the gas molecules are vibrating or colliding with at certain rate, and the measurement of that collision, we can translate that in terms of temperature. So higher the temperature, means the collision is higher. And when that collision is less, the temperature decreases. So we can relate temperature to the motion energy of the particles, atoms, molecules of either gas or solid or liquid. And hot material, so there are two types of material we can associate now, the hotter material and the cooler material. In hot material, the individual particles are vibrating more, there's more rapid vibration, more rapid collision. When the cold water, when we start to boil it, the temperature increases because the vibration or the collision of the water molecules start to increase, and that in turn increases the temperature of the water. And we also know higher energy waves have higher frequency, and the particles have low energy, meaning the atomic and molecular motions are low, and they also generate low energy waves. So that's basic relationship between radiation and temperature. So if a star is hot or a star has higher temperature, it is likely to generate high energy waves, and if a star object is cold, it generates low energy waves. And we define something called a black body. Black body is an object that does not reflect back or scatter any radiation. It absorbs. If we shine any electromagnetic wave on it or any energy that falls into it, it absorbs that radiation. Those objects are called black bodies. But if we continually add energy to a black body, after a while it starts to radiate back all these electromagnetic waves. So now we know what electromagnetic wave is, and when we say electromagnetic waves, it ranges from all wavelengths. Okay, and stars, we can relate it as a black body. It absorbs and it radiates the electromagnetic waves. And now I'm going to compare these 3-4 graphs here, this image. And there are 3 important things to note about a black body radiation, meaning the electromagnetic waves coming out of a black body. A star is a type of a black body, and we'll look at stars at different temperatures. Here in this graph, you'll see in the left hand side, the unit is intensity, and it's the wavelength on the right hand side, or intensity or energy or power. Intensity is power per unit area. Power is rate of energy transfer. They are all interrelated. So again, intensity is power per unit area, how much power is generated, and power has to do with more photons or more light, more intensity. So let's keep it that way. So here, this increasing waves means the intensity is increasing, and the wavelength starts from 0 and goes up to 3000. We're only looking at between ultraviolet, visible, and the infrared region. Okay, 3 important things. At each temperature, so these are the temperatures: 2500, 3400, and 4400, 5500 Kelvin is like Fahrenheit, Celsius, Kelvin is a unit of temperature that we use to measure the star temperature. And in most of astronomy, we use Kelvin as the standard unit to measure the temperature. And so these 4-5 temperatures range here. At each temperature, our black body emits radiation. Radiation is emitting photons. Radiation is also wave, and we say, light behaves as wave and particle both. So we can say radiation means it's individual photons at all wavelengths. So at that temperature here, 2500 Kelvin, we see the black body emitting radiation at around 500 nanometer wavelengths, and the intensity increases at about 1200 nanometer wavelength, and it decreases, but it does cover from visible to infrared. So that's what it means, at almost at all wavelengths. That's one point. An object at higher temperature emits more power. So the objects at higher temperature, so these are for different black bodies. So if that body or if a star has higher temperature, 5500 Kelvin compared to 2500 Kelvin, as you see in 5500 Kelvin, the wavelengths, the power, the object at higher temperature emits more power at all wavelengths. So you see at lower 2500 degree Kelvin, the power is less. So your y-axis is the power. So it has less power at 2500 Kelvin compared to 5500 Kelvin. The power is much higher. So higher the temperature, more powerful radiation an object emits. This later will be translated to stars. The cooler stars emits less power. Hotter star emits high power. And lastly, higher the temperature, shorter the wavelengths at which the maximum power is emitted. So you see the maximum power is emitted for 2500 Kelvin around here, 3400 here, 4400 is around here. So as you increase the temperature, the maximum power generated at each maximum wavelength gets shorter and shorter. So it comes towards the 0 point. And so for highest temperature, the maximum power is generated at that point, which is at the lowest wavelength compared to 2500, 3400, and 4400. And this, a shorter wavelength, means high frequency, which means high energy. And this last statement is called Wien's law. And Wien, based on that statement, he put out a theory that the wavelength at which maximum power is emitted, so the wavelength somewhere here, so this is the wavelength range where the maximum power is emitted, and for that temperature, the maximum power is generated at that point, which results down to about 700 nanometer. And for 4400 Kelvin, the maximum power is generated at that wavelength. And for 2500 Kelvin, the maximum power is generated at 1200 nanometer wavelength. So you see there is a pattern, and based on that pattern, this formula is devised. So we can say lambda wavelength The maximum lambda is equal to some constant, it's a number, 3 million, divided by temperature. So if I know temperature of a body, I can tell where the maximum power will be generated at what wavelengths or vice versa. And this relationship is called Wien's law. By the way, the Kelvin and centigrade relation, 0 Kelvin is same as saying negative 273.15 degrees centigrade. This is also called the absolute zero temperature. Whenever temperature is measure of the motion energy of atoms and molecules, the vibration, collision, and all that. What happens when things stop vibrating or moving? There is no temperature. Meaning at absolute zero, if we can cool down anything to minus 273.15 degrees centigrade, we freeze everything. I mean, we see water being frozen to ice, but there are still the water molecules, the electrons in those molecules are still vibrating. So what it means to say absolute zero temperature, meaning all the vibrating electrons, all the vibrating subatomic particles that we know are made up of atoms, or atoms are made up of those particles, they cease to vibrate, they cease to move. Everything stops. And that is called the absolute temperature. And that temperature is hard to create. We haven't seen absolute zero. We have seen close to that. There's a way to cool down things, and that was the Nobel Prize winning experiment, I believe in 2007 or 8, and it was like few degrees. It was still few degrees above that. It was created in Boulder, Colorado, and that's why physicists call the coldest place on Earth is Boulder, Colorado, because that's in a lab. The lowest temperature was generated. But again, that's 0 degree Kelvin is equivalent to negative 273.15, and if you rise every degree 0 or 1 degree Kelvin would be 1 degree hotter. So that would be negative 272, negative 271. You add 1 degree on the both sides to convert anything. Question for the sun: the wavelength at which the maximum energy is emitted is 520 nanometers. We can measure the light, and we know we can measure the wavelengths of that. What is its temperature, or what's the temperature of this star? Okay, here we know the wavelength. To find temperature, we simply reverse the position, solve for T, and that's about the temperature of the sun, 5800 degree Kelvin. Now, if we can find measure the wavelength of the light emitted by whatever star in the universe, we can use this equation to get its estimated temperature. So we don't have to go there and stick thermometer inside these stars, which is not possible anyway. We cannot even do that for the sun. And we can also measure the total power generated by a star, or we also call that the luminosity, L of a star. And we use the flux equation Flux is power emitted per square meter of a star, is given by Stephen Boltzmann law, which says that flux is equal to sigma, which is a constant, which has a value 5.67 times 10 power 8, sigma times its temperature power 4. So if from the previous equation we can find the temperature of the star, sigma is a constant, we can calculate the energy flux per square meter. That's in 1 square meter area. Now if you want to find the power generated by all of the stars, we just need to find the whole area of a star, which is pi r square, 4 pi r square. Pi r square is the area of the circle. 4 pi r square is the surface area of a sphere. You multiply that with the flux per square meter, we get the luminosity or absolute luminosity, or the total energy, total power emitted by one single star. Next, we'll continue with spectroscopy in astronomy. Here we'll describe the properties of light and measuring the light, or measuring that property of those light, how we can tell the composition of the stars, what elements are available, are present in those stars, can be told by looking at the spectral lines or analyzing the light coming out of those stars. And we'll start with sun. Let's understand the basic properties of light. We're all used to with it every day. We all look in the mirror every day. Mirror uses a property called the reflection of light. When light bounces at certain angle with respect to a perpendicular or a normal, it bounces back at the same angle. That's the reflection property of a light. A mirror reflects more of the light, that incoming light or the incident light, about 97-98% of the light. It is still absorbs that 1%, 2% of the light. Some of the light is so there is reflection, there is absorption, and some is transmitted. Very few percentage of it. The other irregular surfaces like tables, countertops, these reflect less amount of light, so don't form the images because of diffuse reflection. The other property is the refraction. When light goes from one medium to the another medium, it bends, and it's usually visible in a glass of water when you put a pencil on it and you see that pencil bent. That's one example. You're standing on a pool, your leg appears very short. That's also because of the refraction of the light. Okay, and but the other example is the glass, the prism. Because light travels in one path with one speed in air medium, and when that light enters a glass medium like this, I'm giving a prism example here. Prism, the light that we know, or the sunlight, is white. Remember, the light is white. We see different colors, especially of that white light, but that white light is made up of multiple other visible colors, like the sunlight. Okay, when it enters the medium, a different medium, it bends. Okay, but since that white light has multiple other spectrum, multiple other colors, and those colors have different wavelengths, different frequency, different energy, their speed is different, and hence they bend at a different rate. So white light enters glass, they all bend at different rate, different angle, and so now it kind of separates. So that white light that had all these rainbow colors, red to blue or red to violet, they bend at different rate, and when they come out, now they got separated from the white light. Okay, so here this is the refraction, and the phenomena where a light, white light, emerges from a glass particle or water molecules. This phenomena is called the dispersion of light. I say water molecules because if you stand between rain, moisture, water particles, and the sun, when that sunlight hits the water molecules, each water molecules act like a prism, and that water molecules disperses the sunlight into rainbow color, and we see that phenomena as a rainbow. Details of the rainbow, how it's observed, are found in the reference material at the end of the lecture notes. And again, Newton did this experiment. Newton, other than writing down all his Newton's first law, second law, third law, gravitational law, universal gravitational law, finding calculus. In his extra time, he did his optics experiment, and we call this Newton's prism experiment. And so these are, some of the properties of light. If this band here, we can project it on a screen, and that projected screen would look like that. Again, the infrared, UV, our human's eye don't detect that. This is the visible range from 400 nanometer to 700 nanometers wavelength. And one more definition here. Again, this is a spectrum of light, or a spectrum of, when we say light, it's visible light. Okay, so the spectrum of visible light, we use an instrument like Prism is an instrument that is used to disperse the light and create this spectrum. Hence, that device is called a spectrometer. And Prism is a very simple, basic spectrometer. Usually, even a piece of plastic does it. If you have a plastic ruler, you shine it to the sun. You look at, try to find that in the shadow region. You will see rainbow color because light entered from air to plastic medium. It dispersed. Okay. It's more effective it's more visible in Prism. That's all. And this idea, this concept here, the sending white light through a very simple prism, that's the simplest spectrometer. It dispersed the light into a continuous spectra of light, and we saw these rainbow colors. The spectrum of white light from the sun and stars are not simply continuous rainbow of colors. And this was the biggest finding in astronomy. A better spectrometer built by William Woolston 1802, he improved the spectrometer. That included a lens to focus the sun's spectrum on the screen, and instead of just seeing a rainbow of colors like blue, green, orange, and red, he also found these dark lines. Okay, it took few years, maybe 100 years, to finally understand these dark lines, but it had enormous consequence in the study of these stars, our sun, and other stars. So what's happening here is that what these dark bands, the dark lines signifies is very important. As the electromagnetic spectrum or the radiation, as the radiation leaves the sun, it has to go through the surface of the sun or the sun's atmosphere. And when the sun's atmosphere has certain elements, could be hydrogen, helium, lithium, boron, carbon, nitrogen, oxygen, iron. So it has these elements in the atmosphere of the sun, and so when these radiation in that spectrum here, when these radiation hit these atoms of those elements, there could be anyone, these elements or these atoms would observe that spectrum or certain wavelength of that spectrum. Each element would observe only one specific wavelength of light. So for example, these vertical lines here, if it's carbon, let's say, carbon would observe a specific wavelength of that spectrum. If it's oxygen, oxygen would observe only specific part of the spectrum, the wavelength of that spectrum. And when elements observe that wavelength, so it's like eating up that part of the color, and it's dark. And that's why these are called absorption spectrum. These absorption spectrum are created when the elements, specific elements, could be helium, hydrogen, carbon, iron. When these elements observe the certain wavelength of that spectrum, it appears dark. And these are called absorption spectrum. And the other type, there is another type of spectrum called the emission spectrum. This is simply opposite to the absorption spectrum. This was initially done using some experiment in the lab. When we heat up certain elements, certain gas, like sodium, let's start with sodium, or hydrogen. So when this is a continuous spectrum band, that's what it looks like. When we heat specific element like sodium, it gives off wavelengths at these bands only. So here in the x-axis is the wavelength. Wavelength is as a units of distance, which is meters. So here you see A star or A, that is angstrom. 10 power minus 10 meters is equal to 1 angstrom. Just another conversion just to confuse you. But again, this is just the wavelength, length measurement, okay, the distance of the wave. And so when sodium element was heated, it gave off light which had only wavelengths at where it's seen here. So at close to 500 angstrom and around 600 angstrom. When hydrogen was heated, the wavelengths emitted, the radiation emitted by the hydrogen had wavelength at these locations only. So what that tells is, now if this is like my formula, if I take a spectra from a star and plot it like this with versus wavelength here, if my lines appear, the measurement of the wavelength, right, if they appear right here at that location, this is my blueprint, so that means that star has sodium in it. If none of these appear, only the bottom ones here. If the spectral lines of a star looks like this, at the bottom, the composition of this star is more towards Mercury. And that's how the composition of the stars are known without us being ever there. Okay, just two things to point here. The temperature determines whether the lines are bright or dark. Meaning, this one here, the absorption spectrum, meaning the temperature is cooler. Like when the light rays, when the radiation from the sun surface is hot, outside it gets colder compared to the surface. So the radiation has to go through a cooler temperature. So there the absorption happens. So we see dark lines. And any heated gas, higher temperature, the emission happens. That's why these are emission spectrums. But the wavelengths, the wavelength signature from each chemical, each element is the same in either the emission spectra or the absorption spectra. Again, and 1860, German physicist Gustav Kirchhoff, he used spectroscopy. He measured these spectral lines coming out of stars, created the whole length of catalog, especially for sodium. He found the spectral signature. He found the sodium spectral signature coming out of the sun. And when, let's say when sodium gas was heated in the lab, and when its wavelengths were measured, the sodium's emission spectra, this one matched with the sodium spectra of the sun. That's why we know the composition of the sun had sodium. The primary composition of any star is hydrogen and helium, period. Is hydrogen the most? Because it has a fusion reaction, every star has a fusion reaction, otherwise it would not be a star. Fusion reaction means when two hydrogen fuses together, it gives off energy, and when two hydrogen fuses means it has one proton, one electron. You fuse it together, meaning now it has two protons, two electrons. What's that? It's a helium, right? And that helium, when the time continues, there is continuous, that nuclear reaction. So over time, that helium fuses with another hydrogen and now becomes lithium. And that lithium again fuses with another hydrogen to form beryllium, boron, carbon, nitrogen, oxygen. And it goes, the reaction goes up to 26 or so, Fe, iron. So that's how all these elements are produced. They are all produced inside of a star. So we human beings, we have all these elements in our body: iron, magnesium, oxygen, carbon, nitrogen. These atoms, the elements that we have in our body, were produced inside of a star. We are all stardust. We are all particles that were made inside the star.